I'd now like to introduce Monica Chiosa, and she's in her last year as a PhD student in the systems group at ETH Zurich. Her title of her presentation is Putting the Work in Network Stream Data Analytics. Thank you very much. Okay. Excellent. Yeah.
Okay. Hello, everyone. Till we wait for the quantum computing to get from 5 to 95 qubits, let's talk a bit about how we put work in the network. So businesses have adopted cloud computing into their customer solutions because of its flexibility and scalability. But beside these features, the cloud is offering a pool of computational resources, such as CPUs, GPUs, FPGAs, ASICs in the terms of the TPU. If we're going to put on the scale regarding generality versus hardware specialization and power efficiency, in your leftmost side, you will find the CPU, and in your rightmost side, you will find the ASIC. The FPGA finds itself in a sweet spot for generality, hardware specialization, and power efficiency. But the FPGA have been still recently and mostly used as a coprocessor, being connected to the CPU via PCI Express and having a standard computational model. The data gets pulled from the CPU memory, sent to the FPGA, where some algorithms are processing it, and sent back to the memory of the CPU. But the FPGA has itself a pool of digital resources that can be programmed in order to perform different tasks. And such a task is the network one. By enabling the network in the FPGA, we allow it to have access to the network and be part of the system, and further away from the standard computational model and towards a new one, where the data is coming from the network and through its way to the CPU memory goes through a computational kernel. In my research, during my PhD, I have looked at how different algorithms that imply approximation computation or exact computation can be attached to network stacks implementing TCP/IP or RDMA. Today, I'm going to show you how an exact compute algorithm can be attached to the RDMA network. Let's first look at the network setup. So for the RDMA, many of you know that the InfiniBand brings the best performance of the RDMA protocol. But there are many companies that have adopted Ethernet into their cloud deployments and have RDMA over converged Ethernet. For example, Microsoft Azure and Alibaba Cloud are such examples. And also, Oracle Labs have furthered away from the InfiniBand infrastructure towards the Ethernet infrastructure in their Exadata project in order to have larger elasticity for resource utilization. In my research, I have utilized routable RDMA over converged Ethernet, and in the following, I'm going to show you how it is coupled with the exact compute algorithmic kernel. So for the kernel setup, we wanted to have an algorithm that assesses the linear relationship between two or more data attributes, and we want to do it in a quantizable way. Such a measure is the Pearson correlation coefficient that tells us how two data attributes can evolve together. More precisely, if we have a line of best fit that is going through the values of these attributes, the Pearson correlation coefficient tells us how the attributes are varying around this line. Having a correlation computation, the Pearson correlation computation is not just for fun. Actually, it has a quite large usability For example, it is used in machine learning to reduce the dimensionality of the data for training. In databases, it is utilized to enhance the capabilities of the query optimizer. And it also finds usability in data privacy, medicine, physics, and economy. If we look at the mathematical model of the Pearson correlation coefficient for two data attributes, we can see that it is calculated by taking into account the variation that exists within a data stream and how the streams are varying together. But if we work this initial equation, we can observe that the Pearson correlation coefficient for two data attributes can be calculated by gathering a few items. So, these items are sum of elements, sum of squares that are characterizing each data attribute, and sum of products that is characterizing this, the pair of items. By enabling only the gathering of these elements, we are able to calculate the Pearson correlation coefficient in a streaming manner. So you can think at the data as a flow of bits from where you gather the Pearson correlation coefficient information. Now let me walk you through the architecture. It's a simple architecture, but it's a quite efficient one, as you will see later. So imagine that you have an input, as an input, a cache line. This that contains the values of multiple streams. This cache line gets sent for pre-processing, where it is split into the number of streams with respect to their data representation. So for example, if you have a cache line of 512 bits, and each stream has 32 bits data representation, it means that you will have 16 bits processed in parallel. Next, the ACC engine is gathering the items I mentioned to you before, the sum of elements, sum of squares, and sum of products for each of the streams and pair of streams. And when the last item of the element is encountered, the values, yes. So the values get sent from the ACC to the temporary storage that can be the BRAM, from where the coefficient engine starts reading them, while new values are accumulated in the ACC engine. And in the post-processing phase, the coefficient, the obtained results are gathered together into cache line in order to efficiently send them back to the CPU via DMA transfers. Next, I want to give you like a visual representation of the spatial architecture that is taking place on the FPGA. And you can see that on the ACC engine, you have a very large degree of parallelization. The image here is representing only 4 streams in parallel, but it's just to get you the feeling of how large the parallelization is taking place. And the coefficient engine, if the ACC engine has a very large degree of parallelization, the coefficient engine is characterized by a very deep pipeline, which is not possible to have on the CPU. Now let's move up. Before we move to the evaluation, one important aspect of the architecture is that it enables the processing of the input data at every clock cycle. So this means that the computational model doesn't put any back pressure on the previous modules, such it will be the network module. For the experimental setup, I had 2 hosts that communicated via RDMA, where the RDMA stack is implemented on the FPGA. And we kept the 32-bit data representation, so we had to evaluate 16 streams in parallel on an Alveo U55C board. For the CPU baseline, I kept the same data representation and the number of parallel streams, and I utilized a C++ library that is optimized for linear algebra. In this graph, I want to show you the performance of the RDMA-only communication, where and on the x-axis we have the number of streams and the number of items per stream, and on the y-axis on your left side, it is the time that is taken to send over the RDMA network all the data that is required for the for all the streams. And on the right side, you have the throughput performance of the network. If the goal of the previous figure is to show you the network performance, through this figure, I want to show what is the difference between the CPU and the FPGA. And for this, we have three scenarios. In red, we have the RDMA-only communication. Next, the next 4 bars represent the RDMA communication with the correlation computation being calculated on the CPU, while multiple threads are allocated for compute, being them 1, 2, 4, or 8 threads. And in blue, we have the RDMA communication plus correlation computation on the FPGA. And even if for the CPU allocate 8 threads to compute the correlation coefficient, the time to compute the values for 16 streams in parallel are much larger than the communication time. So with the FPGA, we are able to compute the correlation coefficient within 100 microseconds, being very close to the communication time. So it is almost like we are getting for free the correlation computation. There are a few messages that I would like you to take away from my presentation. Is that whenever we have an algorithmic kernel that has an II of 1, there is no throughput penalty that is inferred on previous links. The latency inferred by the pass-through kernel is very small when compared to the time taken to transfer the data. The FPGA correlation implementation outperforms a multi-threaded CPU implementation, and the FPGA is a very good candidate for on-the-fly data analytics. Before I conclude my talk, I would like to bring to you the open source project Systems Group is having in order to facilitate research in the FPGA in the cloud domain. Yep.
Thanks, Monica. Very interesting. Do we have any questions from the audience? No, I have one. Was there one hand comment? No. So, did you ever do any energy consumption, power consumption comparisons between the FPGA implementation and the CPU?
Not for this project, but for other projects we have looked. I think it's a bit difficult to just say it consumed this amount. For the CPU itself, usually you have like something that is plugged between your energy supply and the CPU. But usually when you have an FPGA, you have the CPU connected via PCI Express, you have the power supply of the FPGA. So we considered like the values not to be very reliable. We usually look at what the bit streams are for the FPGAs are not simulate. Yeah, they are using for as a simulation point, but what they are offering in terms of power consumption. But the FPGA tends to be lower than the CPU, from what we have seen.
Yes, yeah. Okay, well that's actually a very, I'd like to just expand on that, because that's a very interesting point she's making. It's extremely difficult to extract some of these direct comparisons of power measurements.
Yeah.
And I mean, just to, you would need a network card, you'd have a PCI bus to the CPU, and then you'd have the CPU running its cores to external memory. Whereas the FPGA, you would roll the network card, the processing, and the memory all in the device. So we're talking serious power consumption. My background is a pioneer in FPGA computing, high performance computing. So it is a really interesting area. And I think that one of the areas we do need to move more towards is being able to get the measurement capabilities, which is what I think we'll hear from maybe the next presentation, to give you some background on that. But this is going to become important. When we put energy first,